Hello everyone, this is Indradeep Kumar, Assistant Professor, IARE, Hyderabad. In our last video, we had seen about the basic concept of stresses. Right now, in this video, we will see impact of stresses due to axial loading. So our topic will be for this video is the state of plane stress. So all the stress component acting along the direction of axis, as we had seen in the previous video, that along the I3, either it's a z axis or x-axis or y-axis, whatever we will assume according to that. So in our previous video, it was for z-axis as I3. Okay, that will vanish when we will consider about the 2D. So that's why as our topic is plane stress, means only we will consider the two dimension. So we are considering I1 and I2, and we are not assuming that I3, means I3 will be vanished, or we can say it's negligible. So what about the non-vanishing? Non-vanishing will be I1 and I2. So along I1, sigma 1 was there, and along I2, sigma 2. So sigma 1, sigma 2, and shear stress along the plane of I1 and I2 will be the tau 1, 2. So when very thin sheet plate will be there, then it's applied just axial load will be there, which we have seen in this figure. So let's see here. Once surface is there, so now we have this figure as 2D only. So in this figure, we can see the two dimension is there. So over the surface, it's acting. So how this over the surface? So just see here. Now, whatever the stress will act in that direction, or force will act, that we will consider. So first along the x-axis, that is delta sigma 1 along x1 direction, because along the x-axis it's acting, so along x direction. Then now that dou tau 2 1, along the plane 2 1 along the x2, that is in x2 direction it will be, right? So that x2 direction, and b1, as earlier we also mentioned that b is the body force, so b1 component along the x-axis. Similarly, for the other one will be dou tau t12 with respect to x1, and now this time sigma 2 will be along the x2 direction, and in y direction the body force is b2. So that must be, for equilibrium, that must be equals to 0. Here we are not considering the z-axis, that is I3, so b3 component won't be there. Now next is surface traction. So that will be T1 for the first axis. T1 will be N1 sigma 1 plus N2 sigma N2 tau 2 1. And similarly for T2, now for the second one, N1 tau 1 2 plus N2 sigma 2. So just see here one. T1 we are taking that surface traction along T1, then there which one is acting? Sigma 1. When we are talking about T2, then it's a sigma 2. And when that is the stress is there, tau 2 1, then next for T2 it will be tau 1 2. So just opposite to that one, here one more thing you have, just how you will remember, T1 then N1 sigma 1, and then the another, that is along the y-axis, N2 unit vector with tau 2 1. Now when tau 1 is there, so opposite to that one, shear stress will act, and in the same direction sigma 2 will act. Like that you can remember. So now here, as we discussed, that this is shown in figure 11, very thin plate is there on which the load is acting. So from this figure we can say that, just see here in this one, N is there. So along this, from this, analyzing this figure, we will get here. So normal vector N will be equals to, now, so we are considering for 2D. So N equals to N1 I1 plus N2 I2. Now what is N1 and what is N2? So that we have to find. So from this figure we can find as what is N1 here and what is N2. So just in this figure, if you will take, then N1 will be here cos theta, N2 sin theta, N3 is 0. So after putting this, what we will get? N equals to N1, that is N equals to cos theta I1 plus sin theta I2. Now tangent to that unit vector. So S will be, so suppose S is the tangent vector. Okay. So then S1 along the I1. So S1 I1 plus S2 I2. Now what is S1? Because just see, tangent to that vector. So here S1 is minus of sin theta again from the previous figure, and S2 is cos theta. So now just substitute these two in the previous that traction equation. So in this equation, we will put those values. So after that, we will get this one, cos 2 theta with sigma, that n1 or n2, depending on which direction, sine 2 theta sigma plus 2 sine theta cos theta sigma. This also we can write as sine 2 theta tau. Similarly, for other equation from this 12, that sine theta cos theta sigma 2 minus sigma 1 plus cos 2 theta minus sine 2 theta tau. So this we have as a from that equation 1 and the previous one, equation of traction. So from those two, after substituting, we will get this values. From this, we have to refer the first video where we derived for this one, and we are substituting here. Now, so it's just acting on an arbitrary phase within the seat, means inside the seat only, not other than that one. So now how we will see, so let's see in this figure. So this is what 2D version of Cauchy tetrahedron. Whatever the tetrahedron is, the tetrahedron is not 2D, but what we will see from the front side or this one in 2-dimensional. So this figure we will have. So now in this figure, we will see how the stresses will act and all. So now just see along this one, so perpendicular to this, sigma will act. Along the surface, that shear stress will act. So resultant of this will be in this direction. Similarly for all the direction, this is along I1, so perpendicular to this one, sigma 2 will act. Along this tau 1, 2, resultant will be here. So for all the three surfaces, sigma 1, so sigma 1 is perpendicular to the surface OB, sigma 2 is the perpendicular to the surface of OA, and along the AB, that sigma n will be there. So when this one is theta, so from this theta also you can see here what unit vector we are getting. For analyzing here also you can find theta. So let's see whatever n1 direction is there, you will get that as cos theta and sin theta. So from here or from the previous figure also you can find these values. So now at equilibrium what happened? Those forces must be either equal both the side, or sum of all the forces must be equals to 0. So now after substituting these value, we are getting this one from the previous equation. Now what we are doing, we are just dividing by ds. So now this will become what? First equation. So this becomes, I'm just writing this one, dx1 by ds, dx2 by ds, ds will get cancelled, and here again ds. Right, now dx1 by ds is what? Our n1, dx2 by ds n2, and here we are just keeping as is dx1 dx2 into 1 by 2 ds. So now here instead of this we multiplied here 2 ds for this equation. So already this is the small, once we are multiplying the very small thing, what happened? This term becomes negligible. So what we will do? We will ignore this term. So now what we will have? Only we'll have this 2 term. Right. So now after put same thing again, just put the values whatever we are getting. So in terms of n1, just now in previous equation we found n1 and n2. So put that value here in both the cases. After that you will get this as tau n. Now projection of that one will be projection in the direction of unit vector, that is n will be projected in the direction of sigma. Then what we will get, sigma of n is sigma 1 cos 2 theta, then and sigma 2 sin 2 theta plus 2 tau cos theta sin theta. Again from this is from the previous equation. So 2 tau sin theta or cos theta sin theta, that we can write as tau sin 2 theta. Okay, so this again from the previous equation after just substituting these value. So now what happened, once we will know about the sigma 1, sigma 2, tau 1, right, then two orthogonal faces allow computation of the stress, means two orthogonal faces should be there, then only we can find. If two orthogonal faces is not there, then we cannot find in which direction the orientation will be there or in which plane we have to find the stress. So two orthogonal plane is required. Now we will discuss about the principal stresses. So already here it is written in from 1.13 to 1.15 we had seen, and from there we got only the sigma 3 is equals to tau 1 3, and which is also equals to tau 2 3, that must be equals to 0. So just substitute that value in previous one, that is in equation 1.31. Then what we will get? This value, right? So dou that this sigma x by d theta is 0. So after the differentiating, equating to 0, you will get tau, that is tan 2 theta equals to 2 tau 1 by sigma 1 minus sigma 2 minus sine 2 theta p by cos 2 theta p. So that just sigma n, it's not here that what is p and all, that's in this which direction we are taking the theta, that is there. Okay, so now after solving this, what we will get? Solution of this one is theta plus pi by 2 will be there. For one, it's a theta, and another one for theta plus pi by 2, corresponding to the two mutually orthogonal principal stress. Means what? For one, if it's a theta, then for other one, it will be theta plus pi by 2. So now just substitute here. And then we'll get the value of what? The minimum or maximum, whatever stress is there. So this will be the minimum stress, that is sigma 1 plus sigma 2 by 2 plus delta, and sigma 1 to sigma 1 plus sigma 2 by 2 minus delta. So this will be adding this term. So this will be the maximum one, and here subtracting. So this will be the minimum stress. So now again, for the maximum shear stress, what? D tau by d theta should be equals to 0. So what we have in previous one, just from here, same equation. Okay, we'll use here. So tan 2 theta is equals to minus sigma 1 minus sigma 2 minus of sigma 1 minus sigma 2 by 2 tau 1 2 minus 1 by tan 2 theta. So let's see from here, sin 2 theta by cos 2 theta. So just taking reciprocal of that one. So sigma 1 minus sigma 2 by 2 tau. So reciprocal of this also will be cos 2 theta by sin 2 theta. So cos 2 theta by sin 2 theta, what we can write? That is 1 by tan 2 theta. That term only is used in the next slide. Yeah. Okay. Now what we have? Theta and theta plus pi by 2. For that we will find. So just put 1 by 1 theta and theta. So with that we will get tau maximum equals to delta, and which is equals to sigma 1 minus sigma 2 by 2. Similarly, theta equals to theta minus pi by 4. Then what happened? Maximum shear stress occur at the face inclined at a 45 degree angle with respect to the principal. So when we are finding the component mutually perpendicular, like suppose this one is there, one is force is acting here, another one is acting here, then the resultant of this will be here, which is acting at the 45 degree. So that only here 45 degree, or you can set pi by 4. That one is there. So either pi by theta plus pi by 4 or theta minus pi by 4. So after finding this, sigma 1 and sigma 2, which will be equals to sigma 1 plus sigma 2 by 2 minus sigma 1, sorry, which is equals to sigma 1 plus sigma 2 by 2 in the principal stress, right? So this is principal stress. Here P stands for sigma 1, that is principal sigma stress in first direction, and principal stress of second direction. So with this we can find how much principal stress is acting on that particular direction. Now rotation of stresses means once the rotation will be there, then what happened? Then still it's not like that static force only. When the aircraft is moving, then definitely some other forces will act also. So at the time of rotation, how the stresses will act, that we will see by here. So again, let's start with the equation 1.31 and 1.32. So by putting those values here, we will get sigma 1 star, which is equals to sigma 1 cos square theta plus sigma 2 sin square theta plus 2 tau 1 2 sin theta cos theta, or you can just write that as tau 1 2 sin 2 theta. Similarly for tau 1 2 will be here, it's the shear stress direction, so direction will be opposite, that's why minus sigma 1 sin theta cos theta plus sigma 2 sin theta cos theta plus tau 1 2 cos square theta minus sin theta. So in this term you can multiply all these two terms, right? Or here also the 2. Then you can write this as minus sigma by 2 sin 2 theta, multiply and divide by 2. So this division by 2 will be there, and here this becomes 2 sine theta cos theta. Similarly here multiply divide, and again this will be plus sigma by 2 sine 2 theta, that is sigma 2 by 2, sigma 1 2 by 2, and here plus tau 1 2 cos square theta minus sin square theta, which is equals to cos 2 theta. So for here that you can also write. So similarly you can further simplify, or directly you can use this also, depending upon the given value which you feel is easier, just you can go with that one. So now for finding this one, that sigma 1 star, sigma 2 star, sigma 3 in the matrix method, how? Just according to this component. So cos square theta, sin square theta, then 2 sin theta, cos theta from here. Then similarly for sigma 2, it will be sin square theta, cos square theta, and now this term becomes minus 2 cos theta, sin theta. And third one we have tau 1 2. So here for tau 1 2, this is what sigma 1 will be there. So we are finding in terms of sigma 1, sigma 2 here. So that's why we are eliminating this one and taking sin theta, cos theta, again sin theta, cos theta, and cos square theta minus sin theta. So this just see here, cos square theta, sin square theta, 2 sin theta, cos theta is there just by multiplying this one. So can be easily inverted by simply replacing theta to minus theta. So once we will multiply theta, that will replace theta to minus theta, again we can invert this whole matrix, right? So now again by solving the matrix method, we can find in terms of sigma 1 how much sigma 1 star will be there, sigma 2 star will be there, and tau 1 2 star will be there, depending upon again the orthogonal phase is important here for those two dimensions. Similarly here sigma 1, sigma 2, and tau 1 2, in those two orthogonal phases only it should be there. Now hydrostatic stress state, hydrostatic means what, right? Then hydrostatic pressure is acting. Okay, so that if suppose that hydrostatic pressure is P, so again same thing we can say that sigma is stress, hydrostatic means it should be fluid. For fluid only the hydrostatic pressure is acting, just like difference we discussed already, pressure and the stress. Pressure is for fluid and stress is for the solid body. So if suppose some liquid body is there, or that body is submerged in some liquid, then what happened? Because of that also stress will be there. So just like considering that as a hydrostatic pressure. So in that case no shear force will be there, only sigma 1, sigma 2, and both will be equals to P. So when pure shear stress is there, pure shear means there is no shear stress, means that time sigma P will be equals to, that is sigma P1 equals to minus of sigma P2, or you can say sigma 1, sigma P1 plus sigma P2 is equals to 0. This will be there. So from figure 1.13, that is here you can see this one. So this will be equals to opposite to that one. Now just here for at this 45 degree also we had seen in earlier slides, that 45 degrees. So just see at the face inclined at a 45 degree angle with respect to the principal stress direction. So principal stress direction is this one, and it's inclined at 45 degree. Then just again same thing, we have to put the theta value as 45. Then we will get tau 1 2 as minus sigma P, and tau sigma 1 star, sigma 2 star equals to 0. So just in this case tau 1 2 was 0, but in case of pure stress sigma 1 star and sigma 2 star will be 0, and only just here the stress will be there. It's a simple meaning by word itself, pure shear stress means there is no principal stress or any other, only the shear stress acting on that body. Now the stress state in thin walled pressure. So now in thin walled what happened? So this is the complete cylinder, just like the example is you can see the fuel tank, that this one petroleum tank here, inside petroleum is there and that having huge capacity, right? Then how much pressure will act because of those fluid, because while moving, if it's that vehicle is constant, then not that much force will affect, whatever the weight of the fluid will be there, that. But once that vehicle is moving, then again because of that these inside the fluid will start moving and they will create pressure on the inner surface of the container. So how much they will create, what strength should be there, that also we have to analyze first before filling that one or before utilizing those things. So how? So just see, when we will cut this part into parts, what we will see, you can say all the surfaces, these parts will experience a stress, and that only helps to find out to by how much stress will act, that we can find, and according to that only we can fill that container. Or if suppose more content, more fluid we require to move, then according to that we will make thicker, or that much strength should be there in that container. So now again in the same plane. So this is sigma in axial direction and sigma h as a circumferential, or you can say the hoop direction. Already we had seen in this one the hoop's stress, how much stress that in physics, that how much stress will act inside of anybody's hollow, then how much it will be there. So now here possibly a shear stress will be there, that is tau ah, means along these two. So earlier like say xy, here we have taken one as a, the other one as h. So this will be along the surface only the shear stress is acting. So tau ah will be in this direction. Now axial force equilibrium. So again equilibrium is what? Whatever the force is acting, that must be equals to 0. So similarly here sigma pi rt equals to pi pi r square by 2. So see here pi rt and pi r square by 2. So pi r square is what? Area, where r is the radius, and pi r is half. That's why here also area half is there, right? So sigma formula is pressure by area, right? So sigma into area must be equals to pressure, right? So similarly pi r square is cross sectional area, but what we have half area only, right? So divided by 2, and here this is pi r is the half or semi circumference. Okay, that's where it's written area of cylinder cross section in the direction of axial load or axis. So after this what we will get? Sigma as the p r square by 2 t. So this is because sigma a pi r t, which is equals to here. So this t will come to this side. So pi will get cancelled, and we will get as sigma pi r square by 2 t. So this is the axial force in equilibrium. Now tangential direction. So the tangential direction is the Hooke's direction. So in this case 2 sigma Vt equals to pi equals to P 2 RB, where again internal area, this is RB, 2RB, internal area of cylinder projected to tangential hoop direction. So this is what? Internal area of the cylinder. Now again from here sigma 2 will get cancelled. So PR by T, and tau will be in this case what? It 0. Now next is Mohr circle for the plane stress. So here we will see just about the concept of the Mohr circle, not exactly how Mohr circle we are drawing. We will see here the importance of the Mohr circle. So by the method of Mohr circle also we can find the principal stresses, but that is drawing and that is not in the syllabus. So we will see only the application of the Mohr circle, not how to find and how we can. So just here already in C is given. So equation 1.49. Okay, so in this stress acting on the face oriented at an angle theta with respect to the principal stress direction, then what happened? Sigma will be, the sigma star will be sigma p plus r cos 2 theta, and pi star will be minus r sine 2, sorry, this is r sine 2 theta, r sine 2 theta, not r sine 2 theta, it's r sine 2 theta. Now, so further put whatever the value we have already got for these values, right? After substituting this, we will get as sigma 1 plus sigma, that is sigma p1 plus sigma p2 by 2, and r will be equals to sigma p1 minus sigma p2 by 2. Right. So now after this, just and r square will be equals to sigma star minus sigma a whole square plus tau star whole square, which will give you the r square value, and this is the equation of the Mohr's circle. where what is sigma star along the horizontal axis, tau star along the vertical axis, that is inverted, right? Center at a coordinate sigma a on the horizontal axis, r radius. So just see in this figure that with this we can draw. So here just to show how we can find by the Mohr circle. So here from the center, this is there, right? This will be the radius. After drawing this part, whatever the projection of this OB will be there, that will give you the maximum shear stress. So similarly for in all the directions, so here this will be your sigma 1, sigma 2, okay? Then same, P is acting here, right? Just see, this is the direction of positive. So that means if in this direction it will move, then positive. So here theta is moving in this direction. You can see theta is we are taking in this direction. So here 2 theta value will be positive 1. So by this we are finding. So every step we have to draw here, then to find the maximum principal. So this will be the maximum principal stress of that one. This is the principal stress. Okay. So based on that we can find. So maximum principal stress will be, already we had seen sigma 1 plus sigma 2 or sigma P1 plus sigma P2 by 2. Minimum will be sigma P1 minus sigma P2 by 2. So just see at point P1. So here is the point P1. Sigma star will be equals to sigma P and tau star will be 0 because there is no stress in that particular direction. So at point E1. So here, okay. Now theta is how much? That pi by 4. Why? Because 2 theta is 90 degree. This we are assuming that angle as 2 theta. So 2 theta is 90. This theta is 40 degree. So for 40 degree we will find, after substituting r, we will get what? Sigma P1 minus sigma P2 by 2, which will give the maximum shear strength. Okay. So maximum shear in that orientation. Now at point A1 and A2, in these points also we can find what happened. Two faces oriented 90 degree apart. So this will be here, whatever the direction will be here from this, the total angle will be 90 degree. The shear stresses are equally maintained. Means just to balance, whatever the shear stress along this will be there, the shear stress along this also will be same, but it is in opposite direction of the this here. So magnitude and of this opposite sign from the principle of reciprocity. Means by this we will get the direction of opposite or principle of reciprocity. By this whatever this will be there, that will be opposite in this direction. So if suppose this value is we are getting positive, then this will be getting negative. So now construction procedure, how we will do this one. So first point A at sigma 1 tau 1 2. So see at point A. So here is the point A, what there we are taking as sigma 1 and tau 1. Second point is what? A2. Here this one just now we discussed, if this one is positive, the other one will be negative. So if here tau 1 2 is positive, then here that will be negative. So sigma 2 and minus tau 1 2. Okay. Next, a straight line joining the A1 A2. So now join these 2 points, right? So this is here. So this point is what? Sigma 1 tau 1 2, and this point is sigma 2 tau minus tau 1 2. So right after finding these coordinates or these points, just meet those 2 points passing through the origin. Definitely that will pass through the origin. So meet these 2 lines. So now stress component at beta and angle. So right. So now this angle. So after taking this, how much just we are taking that as B1, B2 as the point over this one. So now just see here in this case a new diameter B1 O B2. B1 from here, right? So B1 O B2. So now this will be another diameter. Okay, rotated by 2 beta degree from the reference diameter AOA. So our reference diameter was this one. So from this diameter, it's rotated by 2 beta angle. Okay. So now some important features. So principal stresses sigma P1 and sigma P2, that is along the point P1 and P2. Direct stress is what? Either it will be maximum or minimum, right? But shear stress will be 0. So along the principal axis or principal stress, along the point P1, P2 will be either minimum or maximum. So one will be maximum, then another one will be minimum, but shear stress will be 0. Maximum shear stress will be along the vertical line E1. So in this case here, the maximum shear stress will be there, which will be equals to what? Tau 1 2, that is sigma P1 minus sigma P2 by 2 at 45 degree. So what happened? A stress component acting on two mutually orthogonal faces, that is two diametrically opposite points on Mohr circle. So stress component will act here, just we are seeing, along the opposite of two directions. All the points on Mohr circle represent the same state of stress at one point of the solid. So means wherever is there from here, because this distance is same everywhere. So whatever the stress will be there on that Mohr circle represent the same state of stress, because everywhere they are in the same at one point of the solid. So at one point, wherever we will consider on all the direction, it will be same. Means we can say same state of stress will be there on the Mohr circle for every point of the circle. Limbs, ellipse. This is not that much important, but still you should know. That's why just I added this one. So because already we had seen circle, so now circle you have to convert into the ellipse. So for this elliptical, we'll see. So again from equation 1.3, right? So tau 1 to s, now in which direction? So in I direction, and this is in I2 direction. So just with the unit vector is there. So again sigma 1 cos theta I1 plus sigma 2 sin theta I2. In direction also is similar, just here difference will be when we will see this value. This value in this case what happened? It's different, that is minor axis is different from the major axis. So this minor axis, whatever will be there, that, and this will be the major axis, because by seeing itself you can see this is the bigger one from here to here, and this is this one. So here in all the directions it won't be same, like circle already we had seen that for the stress state it will be same in all the direction, but here that is not. Okay, so see in this case what happens? Similarly tau equals to x1 I1 plus x2 I2, where what is x1? So x1 is sigma 1 cos theta, x2 is sigma 2 p cos theta. Now what we have to do, we have to eliminate this theta term, right? So we have to eliminate this theta term. So now what we can do, just divide by x1. So x1 you can see from here, this is x1 by cos theta. So after dividing, what we will get? This square, that is sigma 1 square plus sigma 2 square by this, which is equals to 1, and that gives only this value is what? Along this axis, the major axis, right? Whatever this value will be there. So this is what here? Sigma cos theta up to this, and this is the sigma x. So this is our what? The half of the major axis, and this value, let's see here, this is sigma 2. So half of the minor axis. So this means what? Ellipse formula is what? X square by a square plus y square by b square equals to 1. Here a is half of the minor axis, sorry, major axis, b is minor axis. So similarly here this will be sigma x1, and here this will be sigma p2 x2, which is equals to 1. Actually here sigma p is missing, I think misprint is there, that just because I was putting this one. So sigma 1 p or sigma 2 p. So now this forms a ellipse equation, right? So we can see along this direction it is there. So now equation of ellipse with semi axis equals to sigma p1 sigma p2, just here with this one, right? So this is equation of ellipse with semi axis or semi major axis, semi minor axis. So semi major axis is sigma x1, just wanted to sigma p1 x, and semi minor axis is sigma p2 x. Now pure shear in case of ellipse will be same equals to the circle, which already we had seen. Okay, so these are the differences you can refer. I already mentioned from there some content what I referred. Okay, so these are the references from where you will get these things. If you have any doubt, you can just write comments, or you have my contact number, that email ID and all, you can directly contact me for your doubts. So we will see, either you just comment on the video, so that after seeing that comments I will solve that one, or directly you can contact me on the given details.
Like, share and subscribe. Hit the bell icon for more updates.